This is section 6.8 of Untitled Chapter 2, the complex numbers. When we combine the real numbers, which remember from last lesson are the rational numbers and the irrational numbers together, that's the real numbers. When we combine the real numbers with the imaginary numbers, the numbers that involve the square root of -1, we get the complex number system. A complex number is a number of the form a plus bi, where a and b are real numbers and I is the square root of -1, as it will always be. So we're taking I times a number, and then we're adding on a real number. Notice that if b is 0, then we have 0 times I, which is just 0, and so we just have a then. And a is a real number. So when b is 0, we get the set of real numbers. So the complex number system includes, as a subset of it, the entire set of real numbers. If a is 0, then we just have 0 plus bi, which is bi, and so we get the set of imaginary numbers. Thus the complex number system includes as a subset of itself the imaginary numbers. So it's got the real numbers and the imaginary numbers together. A is called the real part of the complex number, and b is called the imaginary part. Notice the imaginary part is just b, not bi. The imaginary part is the real number that's multiplied by I. So it's not actually imaginary itself. It's giving us the value of the complex number as an imaginary number. We can add or subtract two complex numbers by combining their real parts and their imaginary parts separately. Kind of like combining like terms, where the like terms are defined by whether or not they have an I. So, for example, simplify 3 plus 6i plus 4 minus 2i. Those are two complex numbers. 3 plus 6i is a complex number, 4 minus 2i is a complex number. We're going to add those two numbers by adding their real parts, 3 plus 4 is 7, and adding their imaginary parts. 6i minus 2i makes plus 4i. And that's another complex number. Number 2, 3 plus 6i minus 4 minus 2i. So we need to take that minus and distribute it, make it minus 4 plus 2i. So we've got 3 minus 4, that's -1, 6i plus 2i, that's 8i. So -1 plus 8i. And always write it like that, where you write the real part first and then the imaginary part. Number 3, 3 plus 4i times 5 plus 2i. Now I'm multiplying two complex numbers. We're going to multiply them just as if we had x's and y's in there. We would FOIL it out. We'd multiply it as if we had two binomials multiplied together. So we're going to take 3 times 5, that's 15. 3 times 2i, that's plus 6i. 4i times 5, that's plus 20i. And then 4i times 2i, and that's plus 8i squared, because I times I is I squared. Okay? So that's 15 plus 26i. And then I squared, remember, is -1. So 8 times I squared is 8 times -1, which is minus 8. Okay, 15 minus 8, 7. 7 plus 26i. So the product of two complex numbers is another complex number. Number 4, 3 plus 4i quantity squared. Can I just make that 3 squared plus 4i squared? Absolutely not. Because I'm adding inside. Squaring something means multiplying it by itself. So I cannot distribute that exponent because I'm adding inside. So I FOIL it out. 3 times 3 is 9. 3 plus 4i is 12i, plus another 12i, plus 4i squared, which is really -16. Four squared times I squared, and I squared is -1. So 9 minus 16, -7. 12i plus 12i, 24i. So -7 plus 24i. over 5. 3 plus 4i times 3 minus 4i. Okay, FOIL it out. 3 times 3, 9. Negative 12i plus 12i minus 16 times negative 1. So 9. The negative 12i plus 12i cancels out. And then I've got plus 16 on the end. 9 plus 16 is 25. So that means that I took two complex numbers, I multiplied them together, and I got just a real number. That's because those two complex numbers I started with are called complex conjugates. They are different only by the sign of the imaginary part. I've got 3 plus 4i and 3 minus 4i. It turns out that anytime I multiply two complex conjugates, I always get a real number. I lose the imaginary part completely. The two imaginary numbers in the middle cancel out. The one on the end has an I squared, which becomes a negative 1. That real number I get then is a squared plus b squared. The 3 squared was 9. 4 squared is 16. 9 plus 16 is 25. But you don't have to remember that. You can just FOIL it out. That's useful, because what if I want to simplify number 6? Here I'm dividing two complex numbers, 5 minus I over 2 plus 3i. And the way it looks, doesn't look like I could do much with it. But I can if I simply multiply by the conjugate of the denominator over itself. 2 minus 3i over 2 minus 3i. I'm multiplying by 1, so I'm not actually changing the value of my number, I'm just rearranging it. So I have on the top 5 minus I times 2 minus 3i, and really I need to FOIL the numerators and FOIL the denominators. So I'll have 10 minus 15i minus 2i, and then a negative I times negative 3i is plus 3i squared. That's really minus 3, because I squared is negative 1. Over 2 plus 3i times 2 minus 3i is 4, minus 6i plus 6i, those cancel out, minus 9i squared, which is plus 9. Alright, 10 minus 3 is 7, minus 17i over 13. Okay? If I just simply write that as 7 over 13 minus 17 over 13 times I, then I have another complex number. So I'm able to divide two complex numbers by multiplying by the conjugate of the denominator over itself, giving me another complex number. The real part is 7 over 13, that's a real number, minus 17 over 13 is the imaginary part times I. And always write your answers like that, in what we call A plus BI form. Instead of leaving it as 7 minus 17i all over 13, split it up into two fractions. Number 7. Find the reciprocal of 3 minus I. The reciprocal is 1 over the number. So what's 1 over 3 minus I? Well, let's multiply by 3 plus I over 3 plus I. Okay, that's 1 times 3 plus I is just 3 plus I, over 3 squared is 9, plus 3i minus 3i cancels, minus I squared becomes plus 1. So this is really 3 plus I over 10, or 3 over 10 plus 1 over 10 times I. So the reciprocal of 3 minus I is the complex number 3/10 plus 1/10 I. Turns out every complex number has a reciprocal, and we can find it just like that. Notice, as these examples sort of illuminate, the complex numbers form a closed number system. In the last video, we kept having problems with our number system because there was always an operation it wasn't closed under. The real numbers, for example, were not closed under taking square roots because we couldn't take the square root of any negative real number, which is half of the real numbers, so that's not good. The complex numbers, though, are closed under all of the regular operations. If I add two complex numbers, I always get a complex number. I subtract two complex numbers, I always get a complex number. I multiply two complex numbers, I always get a complex number. I divide two complex numbers, I always get a complex number. I can take complex numbers to powers and always get a complex number. I can even take roots of complex numbers. complex numbers form a closed number system. And that number system is also commutative and associative and has the distributive property. So it's a very nice system, and I don't need to expand it to something larger. There are larger systems, but I don't need them because the complex number system will be able to do most of what I want. Here are your immediate practice problems. 3 problems. Simplify each one. Write them as complex numbers, so in A plus BI form. And that is the end of section 6.8.